content shared on this channel is for informational and entertainment purposes only. Always consult and follow the official and approved aircraft maintenance manuals and procedures provided by the manufacturer or relevant aviation authority before performing any tasks on an aircraft. The information presented here does not replace certified training or authorized technical documentation. Safety and compliance come first. All brakes are subject to wear. Some brakes may also experience oxidation, which can lead to brake rupture. In the case of a brake rupture, or if brakes are too worn, the aircraft braking performance is reduced. This can result in a runway overrun if the full braking capacity is required, such as during a rejected takeoff with an aircraft weight at or close to the maximum takeoff weight. Brake rupture can also lead to damage that can cause a brake fire due to hydraulic fluid coming into contact with hot parts. There are one incident where shortly after landing, the flight crew of an Airbus 330 aircraft heard a strong and unusual noise during taxi-in. When the aircraft reached the parking stand, maintenance personnel observed smoke coming from the area of the left main landing gear and informed the flight crew. The fire brigade arrived but did not see any fire. The flight crew noticed a 400-degree stack temperature on wheel number 6. Maintenance personnel performed a quick inspection of the landing gear, which revealed that one of the brake pistons of wheel number 6 had twisted and dislodged from its housing with evidence of a hydraulic fluid leak. There was no sign of fire on the landing gear structure and components. The investigation showed the most probable cause was a rupture of the brake pressure plate during brake application. The brake piston pushed through the pressure plate and came into contact with the first rotor. This applied a lateral force to the piston, causing it to be dislodged from its housing and causing the hydraulic fluid leak. The hydraulic fluid that leaked onto the hot parts of the brake created the smoke. The pressure plate was found to be significantly oxidized, which was the reason it ruptured when the brake piston pressed against it. Brakes are subject to two different phenomena: wear and oxidation. Brake wear is the progressive loss of width on the brake discs due to friction. Brake wear on carbon brakes depends on the number of brake applications and on the brake temperature. Each carbon brake type has its own temperature range for optimum operation and its temperature range for maximum wear. The temperature range varies from one brake manufacturer to another. Brakes are guaranteed to provide sufficient braking until the brake wear indicator is flushed with the reference surface. If the indicator is below the reference surface, the brake discs are too worn, and the braking performance can be significantly reduced. If the brake discs are too worn, their width is reduced. As a result, the pistons do not have enough extension to push the discs and create sufficient braking friction to slow down the aircraft. In addition, if the brake is too worn, the amount of heat sink mass that is available to absorb braking energy is reduced. In the event of a high-speed rejected takeoff, this can lead to increased risk of runway overrun or brake fire. Carbon from the brakes naturally combines with oxygen from the ambient air to become carbon dioxide, CO2. Under normal circumstances, the oxidation occurs at a very slow rate. However, the rate of oxidation can be accelerated by external factors such as high temperature and catalytic chemical pollution. This results in a loss of carbon mass from the brake discs, carbon softening, and delamination. It can ultimately lead to brake rupture if an affected brake is not changed in due time. Carbon oxidation due to exposure to high temperatures is referred to as thermal oxidation. When carbon oxidation is due to the presence of catalysts, it is usually referred to as catalytic oxidation. Thermal oxidation is the main cause of accelerated degradation of carbon brakes. It can occur if high brake temperatures are reached after landing and during taxi. Thermal oxidation affects all brake discs, but the middle discs are most affected because they reach a higher temperature and take longer to cool down. Worn brakes tend to reach higher temperatures, making them more prone to the effects of thermal oxidation. Catalytic oxidation of the brakes is generally caused by contact with de-icing or cleaning fluids. The potassium or sodium coming from some aircraft and runway de-icing fluids acts as a catalyst and further accelerates the oxidation. The presence of the catalyst also reduces the temperature at which significant oxidation occurs. When the potassium or sodium is absorbed by the carbon, it remains within the material, causing catalytic oxidation to continue well after the end of the winter season. The outer discs, including the pressure plate, are most exposed to external pollution and are usually more susceptible to catalytic oxidation. In addition to high maintenance costs, brake oxidation can lead to brake rupture and a loss of braking for the affected wheel. If maximum braking is necessary, such as in the case of a rejected takeoff at or close to the maximum takeoff weight, it may result in a runway overrun. Brake rupture can also damage brake pistons and lead to leakage of hydraulic fluid. The fluid may vaporize and create smoke if it comes into contact with hot components. This could result in fire. The hydraulic fuses will limit the amount of hydraulic fluid lost, and the fire should remain contained to the brake, but damage may be caused to nearby components. Maintenance personnel and flight crews both have a role to play to prevent brake rupture. There are a number of ways to identify worn brakes and prevent brake rupture, including visual checks, inspection, and taking precautions when using de-icing or cleaning fluids. Regularly check the brake wear indicator. The maintenance planning document, MPD, requires a regular visual inspection of the brake wear indicator to assess the level of thickness loss of the brake discs. The check must be done with the braking applied, parking brake on or pedal pressed or bite activated. If the brake wear indicator is flushed with the reference surface, the brake unit must be changed. Some operators are more exposed to the risk of brake rupture due to their specific operations. Airbus proposes an optional brake inspection with the wheel removed. This inspection was developed together with brake manufacturers and can be added to the AMM procedure by request of the operator. Steps were added to the brake inspection procedure that require measuring the outer perimeter of the central stator, Safran landing systems and Messier Goodrich brakes, or the radius of the friction surface, Collins aerospace brakes. The reduction of this measured value provides an additional indicator of brake oxidation. Airbus encourages operators to report any brake damage or rupture through the Tech Request tool using the brake disc failure reporting sheet available in the AMM or MP procedure for brake inspection. When cleaning the aircraft or performing de-icing, particular care should be taken to prevent fluids coming into contact with the wheels and brakes. Always follow the AMM, MP, AMP procedures for cleaning and de-icing and protect wheels and brakes to prevent them from becoming contaminated with chemicals that will accelerate oxidation. The flight crew can detect worn brakes before the flight during the exterior walk-around. They can reduce wear and oxidation by using the brakes in an optimal manner during taxi and landing. A quick check of the brake wear indicator during the exterior walk-around will determine if the brakes are worn. If there are only a few millimeters remaining before the indicator is flush with the reference plate, inform maintenance personnel to anticipate and plan for a brake replacement before the wear limit is reached. On A220 aircraft, the flight crew can also check the brake wear status on the EICAS status synoptic page. Flight crews should reduce the number of brake applications during taxi to limit brake wear. The Flight Crew Technique Manual and Flight Crew Operating Manual recommend that on long, straight taxiways and with no ATC or other ground traffic constraints, the pilot flying should allow the aircraft to accelerate to 30 knots of ground speed and then use one smooth brake application to decelerate to 10 knots. Maintaining idle thrust during taxi enables a reduced number of brake applications to keep the aircraft below the 30 knots maximum taxi speed. Single-engine taxi is a fuel-saving initiative that also reduces brake wear because it further reduces the idle thrust during taxi. The number of thermal oxidation reports is increasing, especially on the A320 family fleet. This phenomenon may be linked with efforts by many operators to save fuel. It was observed that a majority of operators reporting high thermal oxidation were using flap config 3 and thrust reversers on idle at landing. There is a trade-off between fuel savings, engine maintenance costs, and increased brake replacement due to higher rates of oxidation. This will depend on the flight conditions, aircraft condition, and the operator's policy. The use of flaps full at landing reduces the approach speed and therefore the aircraft energy to be absorbed by the brakes. When auto brake is used and if conditions permit, the use of auto brake low reduces the heat of the brakes and therefore reduces the likelihood of oxidation. Maximum available braking performance is necessary to prevent the risk of a runway overrun in an event such as a rejected takeoff with a fully loaded aircraft. Brakes need to be closely monitored to ensure that they do not have excessive wear or oxidation that will affect the braking performance of the aircraft, or to ensure that they do not degrade to a condition that could cause a brake rupture. The flight crew or maintenance personnel can quickly check brake wear during the exterior walk-around inspection by looking at the brake wear indicator pin on each brake unit. If the indicator is flush with the reference plate or below it, the brake must be changed. It is important to perform a careful visual inspection of the brake assembly at every wheel removal to check for signs of excessive oxidation. Operators should consider adding the optional inspection check developed with the brake manufacturers into their AMM-MP. Flight crews can apply a number of recommended procedures and techniques to help reduce the rates of brake wear and oxidation. This includes reducing the number of brake applications during taxi, applying techniques that will reduce braking energy at landing, and using brake fans when available. These operational and maintenance considerations will ensure that the brakes have a longer service life and are in a condition to create the necessary friction for optimal aircraft braking performance.